Recording. Okay, so today we had a break in between. We didn't really do a January meeting right after the holiday. I thought a lot of folks are probably still in the holiday mode. So this is a meeting after our December meeting, and if you recall, in the December meeting, Hamad present some of the analysis by using a reverse power curve, try to improve the quality of the wind data measurement. And there's quite a bit of discussion. I think Brian, at that time, Brian is not here today, and also suggest a different kind of data set and could possibly be used test on the idea. So today, Ahmad is going to start with a presentation, address some of the questions from the last meeting, but also try out for the new data set. So we're going to let Ahmad to start his presentation first, and then I think we're gonna have another like 20-25 minutes for discussion. Okay. So Ahmad, the floor is yours. The screen is yours.
I'm sorry.
The slides looks good.
Sure. Hi everyone. My name is Ahmed Chokhachian. I'm a PhD student in Professor Yudin's lab in Georgia Institute of Technology. In the last meeting, we came up with a model to estimate the free stream wind speed, and in this work I will have a recap on that idea, and then it will be followed by some extension, and we also try this method on a new set of data set that we will discuss. So the problem we wanted to address was the nozzle data that might be affected by wake effects or flow distortion, and we wanted to see if we can create a model, machine learning model, that can have a better estimate of the free stream wind speed and the turbines. There was two critical assumptions that we made. One was that met tower measurements are less affected by wakes, and so nanometer data of the met towers are from better quality. The other assumption is that if a turbine is very close to the met tower, we can really we can really use the tower's speed data as turbines free stream speed, and that's like a small distance around 200 meters in a wind farm will not really change the speed data that much. So the motivation behind was that if in an ideal wind farm we have several turbines, in an ideal wind farm we have one met tower beside each one of them, and if so, we can really use the nanometer data as wind speed on the turbine. But unfortunately, that's not true, and in most wind farms we have only one or a few met towers. That really motivates us to create a machine learning model on one set of turbine and tower, and then use that model for making predictions on different turbines. But in this work, we're gonna build the model on one set of turbine and tower and then validate it on the other set. So we just want to know if the output, the predictions from our model is better than the nozzle data, or closer to the free stream wind speed or not. So this work had several key steps. Initially, we started from creating a reverse power curve model on turbine 1 and met tower 1. So we just use the power of the turbine 1 as input feature, and then responses, free speed, and tower 1, clearly the non-meters speed. And then we use this function to predict and the turbine to met tower 2 set. So again, power 2 as the input feature, make predictions, and we call it estimated speed. Then we can just, we need a criteria to measure how close the estimated speed is to the free speed and turbine 2. We can use the RMSE criteria, and we call it RMSE model. But the alternative is not doing all this stuff and creating a model, but just using the Nussel data. So the alternative RMSE Nussel will be compared with RMSE model. If RMSE model is smaller, that means our model really is able to make better predictions, and the predictions are closer to the free stream speed. But if not, that shows the Nussel data is doing a better job. So we discussed this method on EDP dataset. EDP dataset had 240 turbines and 4 met towers. Some of them was around 3 years data, and some others for 4 years of data. In the last meeting, we saw the motivation in everyone to take a look to this data set. So we just published it, pre-processed and published it, but only the paired data set. So we paired each met tower with its closest turbine and matched the timestamps, and then did some pre-processing steps and published it. So if you want to take a look to the data, please feel free to use the links I provided in this slide, or if you just search Professor Uding's personal website under the DSWE datasets by scrolling down in the extension datasets. The first one is called pair turbine and met tower dataset. If you click on the link, it will be just open the Zenodo, and in the Zenodo we have two files. One is a report of the pre-processing, which explains the variables and the actually paired data sets. The other file, the zip file, has 5 CSV files. One is the location of turbines and towers, longitude, latitude, and the other 4 CSV files are the data sets. So some variables from column D to column K in this Excel are the tower data. Last 2 variables are the Nussel data, wind speed, and variation of the wind speed. And also we have the power and the standard deviation of the power in this data set. So please feel free to use this data for your own methods and so on. In the last meeting, we also addressed some questions. The most important one was that to see if this model actually works, and how this model is compared to Nussel data and EDP dataset. We saw that model's accuracy is 7% better than the Nussel speed, and I'll have one more slide on this later. How I will explain how this 7% is calculated, and then the other thing we explored was including additional covariates like standard deviation of the power or air density. So one of the challenges with the reverse power curve model we saw was only having one covariate power. We expected if we add more covariates, actually some of them we don't have them in EDP dataset, but some of them like air density we had. These, at least adding these covariates, did not help model much to gain a better accuracy compared to Nussel. And the other question we addressed was to which machine learning model should we use for this task. We tried a variety of the models, but at the end, TwinGP and XGBoost both worked well. 20GP is just a larger scale Gaussian process, which is really quick for large data sets. So for 100,000 data points, it can process it under a minute. And finally, one of the audiences, Mr. Brian Creamy, asked that what if we just limit the data to valid wind sectors? Uh, the motivation behind is that Met Tower data might also be affected by the weight condition. So if we limit the data to valid wind sectors, it might help the model to achieve a better accuracy.
So, Hamad,
Yeah.
let me inject here. On the second point, does including more chloride in additional power enhance the model's performance? Here, our observation is based on the type of additional variable we could put a hands on, right?
Yeah.
There's the conclusion is not mean to say, there's no need to include additional factor, it really depends on what kind of other factors we have available. And from the physical point of view, if you have like a rotor speed, if you have blade angles and those kind of things, it's more likely could provide additional explanation power to make the model more accurate. But just for this kind of wind farm data, which do have at least the two Met Tower allow modeling and validation, and we don't have that additional information. And for whatever the correlate we have, we tested on, and including second data set later, we also test on the yaw misalignment or yaw measurement. That doesn't really have a much significant impact to improve the prediction of wind speed using power, the reverse power curve part. I just want to add the clarification on that point. Okay,
Thank
go
you.
ahead.
So we want to have a second look at this model. About that 7% gain of the model over Nusselt data, we have the power curve in this slide. So there is 3 regions before cutting speed, which the power production is more or less 0 for most data points. Then after the rated speed, the power is max, and then the region between the cutting and rated, this model, the reverse power curve, actually can be fitted in the middle region. So for the other 2 regions, the model is not applicable. I mean, we can try it, but it will not do a great job because for one, because it's actually for same input, there is multiple outputs, and it will be not with high accuracy. So in this work, we have just substituted the RMSE nacelle for those regions. So for RMSE nacelle, we calculate the RMSE of nacelle data and the nacelle data and free stream wind speed on second set. For RMSE model, for two regions of higher than rated speed and lower than cut-in speed, we still use the nacelle data and comparison to free stream. But for the region from cut-in to rated, we use the output of machine learning model, the inverse power curve function. If we do calculate RMSEs for the whole data, RMSE model has only 7% gain over RMSE nacelle. Even though for only the region from cut-in to rated, if we filter the data to only that region, RMSE model is 22% smaller than the nacelle. But still, we use the whole data as a baseline. So for the next slides, also we have this approach, just using the reverse functions predictions from cut-in to rated speed region. Also, we explored the valid wind sector analysis, and so we filtered the data and take out the plus minus 15 degrees of the wind direction which coming from the turbine to the mast, and both RMSEs became smaller slightly, but our conclusion, which RMSE model is 7% better than the nacelle, did not change by this filtering. So at least in this data set, valid wind sectors did not help the model to gain a better accuracy. Next, we in the last meeting, one of the audiences shared a set of data sets, and we explored them one by one, open data. Most of them really do not have mass, or at least they do not have two mass. Only number 11, Noraker Wind Farm, had two mass, and uh, I the requirements for our work is not only having two masts, but also we need to have two turbines close to those masts, and also for the covariates we need speed, power for turbine, and the speed for the mast. So all those features were only in number 11. This is an old wind farm in Denmark, I believe, the Nordic wind farm, and the layout has M1 and M2 as mass. The variables, in addition to power and speed, we had yaw misalignment. As Professor Dane mentioned, uh, if we had more variables like rotor speed and others, we could try them to see if there is a benefit or not. But here, unfortunately, we only had yaw misalignment, which I will show the results in the next slide. The data size after timestamp matching and pre-processing was only 20,000 left, because the whole data is just for 1 year. It's around 52,000. After all those things, not large data left. This is actually in EDP, we had 3-4 years of the data, so the data size was much larger. The other issue we had in this data set was, if you take a look to the layout, A1 and F6 are the closest turbines to M1 and M2 mass, but unfortunately the power data for those turbines were not available, so we had to move to second closest turbines, A2 and F5. We tried different scenarios. On the table we have in the left, we tried it for all wind sectors, and we have with yaw misalignment, without yaw misalignment, and with cosine of yaw misalignment. Seems any transformation on yaw misalignment or inclusion or exclusion is not really changing the results much. So more or less the RMSE model is robust to having this variable or not. Then we also tried it for valid wind sectors. Both RMSEs this time became much smaller, but still the conclusion is over there. So it seems our RMSE model on this data set is not smaller than RMSE nacelle. And it is not even that larger, but it's just slightly bigger. So in valid wind sector with yaw misalignment, they are the same, RMSE model and nacelle. But our conclusion on EDP does not, we cannot make the same conclusion here for the Noreker wind farm. Finally, to conclude, so we tried the reverse power curve function on two data sets, EDP and Noreker. The conclusion was not confirmed on both of them. So on EDP, the model's output was better than the nacelle wind speed measurements, and it had 7% smaller than nacelle. On Noreker dataset, it was slightly bigger than the nacelle data, and using the power curve does not have a gain or benefit. Finally, we discussed that using the valid wind sector really does not changing these conclusions, and is not helping our model to gain some more accuracy over the nacelle data. That's all. Thank you for your attention.
Okay, thank you, Hamad. So we have at least a half hour left, and we'd like to open discussion. If you have any comments and questions, um,
Yeah, I'm sorry, my mouse is not working.
well, I suppose the thing is, we initially thought the reverse power curve would be able to produce a wind speed result better than using the direct measurement on the cell, right? When we do that one-on-one, the EDP data set, it does confirm measurable, sizable improvement. But when we apply it to a second data set, that the benefit was not there. It's not really much worse. It's about 2% worse. But on the other hand, it doesn't see that kind of benefit showed on the first data set. And understandable, the Noric data set is very old. It's on different type of turbines. The EDP data set is also pretty old. It's like 15 years older, and from now, right? The first project is start 2008, and second phase 2009. They finished roughly about 2011. So it's also decades old technology and the project. It's still newer than the other data set. Is that the reason behind, we don't know for sure, right? And maybe you have some experience, can share your thoughts on those kind of things. And maybe, in order to have a more robust result, by using power alone is not enough. You have to use something else. And that something else probably need to come from more kind of reliable measurement, like we mentioned earlier, like rotor speed, right? That measurement itself was not really being called into question, or things more related to the wind speed rather than indirectly related to the wind speed, right? So unfortunately, at this moment, we don't really have many other data set which allow us to give it a try. If you have from either your experience from other open data source, or something from your current work you are willing to share, either the data or the insights, that'd be very much appreciated. Any comments?
Yeah, I can just say thanks from my side. I think it's an interesting investigation. I'll try and take some time at some point to play around with the data myself. At this point, I can't think of any immediate questions or comments to raise. I'm also not aware of, or at least not on top of my head, I can't think of any other data sets that would be useful for this. Like I think I commented during a previous meeting in Europe, it's not so common to have big wind farms with multiple power performance measurement masts.
I see. Right. Only for the model validation purpose, we need a second mast. So once the benefit is established, you only need one mast to do the actual operation, or actual estimation. But in order to validate that claim, I don't really see what else we can do without a second mast.
I want to ask about the hub heights. Is the hub height of the MetMast and the nacelle, are they the same?
I'm sorry, can you? I didn't get the question.
The heights, the hub height
Yes.
of the nacelle
Oh,
and the
For mast, we have different heights, but we take the one which is closer to the turbine's height. So
yes, and how similar are they?
I think it's 80 meters, around 80 meters for both of them. Yeah.
I believe
both
it's the same. They have one of the wind speed measurement exactly at the hub height.
Okay, okay. I mean, just off my mind, what comes to my mind is now that we have the measurements at different hub heights, we could maybe try to include effects of, I don't know, shear. Maybe you could try to calculate the shear and see if that is that filtering or accounting for shear, is that leading to a better correlation or reduced RMSE, or just a thought from me. Because when you have multiple hub height measurements, you can try to get a shear or something.
If you think about how this can be actually used, right? You establish a reverse power curve. Right now, it's not really use the shear to predict the power. You want to use the power to predict the wind speed, right? And when you go to a new turbine, there's around that turbine, there's no other mast anymore. There's only power over there, right? So even you establish the shear can be used, but for that new location, you don't have that information anymore. So I'm not really sure because you still have, if you have rotor speed measurement, you're still going to have over there. If you have the blade measurement, it's still going to have over there, right? You have for example, temperature, air density, you have the turbulence. You could still have those kind of things on that particular turbine. But that shear, like you said, you have multiple, and unless you have another mast tower next to that, otherwise you're not going to have that. But if you do have a mast tower next to that turbine, you would rather better off just use the mast measurement directly, right?
Now, what I was thinking was more like doing this whole analysis only for certain values of shear, or I mean, in that case, it would be using information from the mast, which we might not always have, but just to see if we can eliminate other effects and then see if then the correlation is better. If we reduce the whole available data set to certain values of shear or something.
Yeah, we didn't do that. That's not difficult to do, right? Because in this particular case, we do have two masts. We can use the one mast to feed that one, and then to use the other mast to test on that. I very much kind of skeptical that mast itself, the shear itself can make the reverse. For the forward, I can see why it will produce a benefit prediction. For the reverse direction. I'm kind of skeptical, but we can give it a try, right? We can give it a try to see how that. And the bigger question is really, even you have that benefit, in reality, it's not going to be useful.
Yeah, that's true. That's true. In reality, it's not going to be.
Yeah.
Good work, Ahmad. It's interesting to see that it's the correlation. Nice study. Yeah.
Right. So I think the two set of data set many years apart. The second data set is much older. It's another decade older, which means it's really kind of 20 to 25 years from now. Could be the reason behind. But without another newer data set, it's hard to verify that. Yeah, if that's one of the things, if this group, someone has a newer data set, can validate that claim, I think that will provide some comfort. So I forgot to mention one thing. I sent an email to the group of folks signed up for this workspace, and you probably already all received the email from Sarah Barber about the new wind location. So for us, that's primarily used for archive all these slides and the presentation. So, and I'm not really sure how long that old site is still going to functioning, or maybe it's already being shut down or disconnected from being accessed. So from this point onward, and all the old archived presentation slides, and together with today's and also next month's presentation and slides, is going to be on the new site. And it's pretty easy to access, and the whole process doesn't really change that much. It's just a different kind of interface. You need to make a few clicks and you will find those things. Yeah. For the, the coming months, if you recall, back in September last year, I think Alex from RES, don't remember which company it was.
Yeah, Alex Clark, or you mean?
It's yeah, I think most
Yeah,
likely.
yeah, he's from RES, yeah.
Yeah. So he presented one of their own analysis by using actually exactly the same type of data we provided, and we did some additional follow-up work on that particular part, and we were able to make that combine some of his ideas, combine some of our idea. I think we can make the result even better. His result is one of the very competitive. And as compared to the current result we have, when applied to those the existing data set we shared for this workspace. And so Hamad is going to, give a presentation on that particular part. And if that can be done by one presentation, and this is probably going to just conclude, our series of the on this particular workspace, and we're going to cancel April's and May's presentation part, unless some of you have something you want to present. We're going to reserve that space time, and just in case someone to say, I have something I'd like to share with the group, right? But we can decide that in March, and also another possibility is if there's more interest and questions about Ahmad's work and on combining the different ideas, we might just do a follow-up on April, right? But I think our collaboration activity on this monthly basis is about to conclude more or less toward May of this year, and that really lasted about 16 months, right? 16 meetings, because we have some of the months we skip the meeting, like January, right? So that's I appreciate that you stick with the series this long. I know it's not easy. You're all very busy. Okay, if no other questions and comments, it looks like we are very efficient today, and we only use the half of the time allocated, and you get another 25 minutes back. And I hope you enjoy your day and or even. Okay. We'll see you in March. Thank you.
Thank you.
Thank you.